Welcome once again to my YouTube channel. Today we are going to look into an interesting topic in physics, quantum physics precisely. So we are going to look into energy quantization / energy level. We have a question on the board, but before we solve this very question, I would want us to know more on that energy quantization. Now, in classical physics, we were meant to understand that energy is being emitted continuously. But today, from the study of Max Planck in 1900, that's 19th century, we were meant to understand that energy is not emitted continuously, rather in a small unit, in a small packet, as in a discrete quantities called quanta. When radiations such as light emit such energy, that energy should always be in a whole number multiples. No fractional energy is obtained, rather in packets. Now, this packet of energy emitted by light, which we termed photon, but generally in electromagnetic radiation we term it quanta. That packet of energy is termed what? Quanta. Now, when the energy is emitted, the magnitude of it depends on the frequency of radiation. That means, from the study of Planck, we noted that energy of electromagnetic radiation is directly proportional to the frequency of the source. Mathematically, we have it in this way: energy of electromagnetic radiation is directly proportional to the frequency of the source. And from equation, when converted, we have h as a constant, f as a frequency. So from this very formula, we note that frequency is equal to speed of that electromagnetic radiation over wavelength. So we can also do substitution here from this very formula that energy of electromagnetic radiation is equal to h, where f is c over wavelength, we have c over wavelength. We have this again as a formula. Now, these parameters we have E represents energy of electromagnetic radiation. The energy of electromagnetic radiation. We have lambda as the wavelength. Wavelength is measured in meter. Of course, you know that energy is measured in joule. Then we have h as the Planck constant. So we call it universal Planck's constant. Now, the unit of it, if you make h the subject, it becomes energy over frequency. And energy is measured in joule, while frequency is measured in per second, although hertz. So if you divide joule by per second, you are going to get joule seconds. Joule second. So we have it as a unit. Then we have C, although before this, the H as a Planck constant, it has a specific value. The Planck constant here is equal to 6.63 exponential minus 34 joule second. Then again, we have c as the speed of electromagnetic radiation. The speed of electromagnetic radiation. The speed is measured in meter per second. Now, we also have f as the frequency of electromagnetic radiation. The frequency of electromagnetic radiation. Frequency is measured in hertz. Now, with this formula, you are good to go in solving such an exercise. Now, before we move into the exercise, I would also want you to know energy levels. Now, from the idea of Nebor, the energy, we have orbitals around the nucleus of an atom. So, if we have here as the nucleus, proton and the neutron located inside the nucleus. So, if here becomes the nucleus of an atom, then Nebor made us understand that there is a fixed orbit where electrons are expected to move. He referred it as electron shells. So he has first electron shell, second electron shell, third electron shell till infinity. This electron shell number represents the quantum number, which is n is equal to 1, n is equal to 2, n is equal to 3. Then outside this atom, we have it at infinity. N is equal to maybe 0. Okay. Now, these lines represent the electronic shell orbits where electrons move around. Now, these electron shells can as well be referred as energy level. Now, we have the first energy level. We have the first energy level. We have the second energy level. We have the third energy level till infinity. Now, coming back to the first energy level, this energy level is very stable for any electron that is found there. Now, the stable orbital here is known as the ground state energy level. The ground state energy level. Hence, any electron found at this very first or the ground state is said to be stable. Now, when electrons are found here, those electrons are so stable that only thing that will make them to leave that very orbit is when they absorb energy. Now, if energy of radiation is absorbed by electron found at this level, that's the ground state level, that very electron becomes excited. It becomes excited such that it will jump up to the higher energy level. Now, when an electron situated at this ground state absorbs such an energy, that very state at which it will jump to is known as excitation state. So in that very case, the electron shell above the ground state is referred as excitation state. Hence, the energy of this state is now referred as excitation energy. Now, the excitation starts from the point where we have n equal to 2. Hence, we now refer this as the first excitation energy. From ground state, when electron jump from here to here, this is first energy level. So from here, If electron jumps to this very point, here it now becomes the second excitation energy. So E1 means first excitation energy, E2 means second excitation energy. Now, the energy required to transition electron from lower energy level to higher energy level is what we call excitation energy. Now remember, when electron absorbs such an energy, that electron will get to that very state and will never be stable again. Hence, when that electron loses such an energy in form of photons, that very electron will return back to that very ground state. Now, when electron returns to the state, that electron also vibrates in form of electromagnetic radiation. Now, when electrons at the higher level is jumping downwards by vibrating that very energy in form of electromagnetic radiation, we say that that electron is the excitation. So the excitation now becomes the opposite of excitation. So excitation simply means jumping from lower energy level to higher energy level, while the excitation means jumping from higher energy level to lower energy level. Now, when electrons jump from lower energy level to higher energy level, and you now want to get the energy at which the electron jumps, which we call excitation energy, then the formula now becomes energy of that very electron now becomes energy of higher level minus energy of lower level. And that will give what? The energy difference. And hence, for us to calculate energy level of this, we can adopt Nebel's equation. We have E, that's the energy level, equal to, we have R as a constant all over Na squared. Although with time, we look into this problem. So, that excitation of electrons, which is the what? The jumping up or the transition of electrons from lower energy level to higher energy level. Most of the times, electron will absorb such an energy that will even make it to transit above or leave the atom entirely. When electron transition takes it outside the atom, such as being here, at this very point, that electron is now free. Hence, we say that the energy required for such an electron to leave the atom entirely, we call it ionization energy. Ionization energy. Get the difference between excitation energy and ionization energy. Excitation energy, the energy required to transition electron from lower energy level to higher energy level, while ionization energy is the energy required to transition electron from lower energy level out from that very electronic shell. Hence, that very atom that absorbs such an energy is said to be in ionic state. Okay, with the analysis, I would now want us to get to this very exercise. So the exercise says, the table below gives some of the energy levels of a hydrogen atom. The energy levels of a hydrogen atom. We have their quantum number, N. 1, 2, 3, 4, 5, 6. That means we are going to have 6 electronic shells. But in this very case, we are going to represent it with a line. The we have also the energy equivalent of each of electronic shell. You see the energy equivalent. So the question says, draw the energy level diagram for the atom. So we are going to put up a nice diagram for that. Then the second one says, determine the wavelength of the photon emitted when electron goes, that's when electron goes from the energy state Na4 to the ground state. When electron goes from the energy state Na4 to the ground state. Okay, so let's start with number 1I. They said, draw the energy level diagram for the atom. Solution I. Now, from what we have n equal to 1, 2, 3, 4, 5, 6. So we are going to have 6 lines here. Maybe we have 1, 2, 3, 4, 5, 6. But here I'm going to make it a dotted line because here represent the infinity. So at this point, we have n equal to 1, we have n equal to 2, n equal to 3, n equal to 4, n equal to 5, and finally n equal to infinity. The second excitation energy, the third excitation energy, the fourth excitation energy, maybe we have the zero energy. So we have the diagrams. Now to the ground state energy, we have n equal to 1, we have here minus 12.59 electron volts. Then here we have minus 3.59 electron volts. We have minus 3.25 electron volts. And then n equal to 4 here, we have minus 0.76 electron volts. While here we have minus 0.45 electron volts. And at this point, we have 0.00 electron volts. Now, this diagram represents the energy levels. And that answers the question of number 1. Solution 2. Now we are asked to determine the wavelength of the photon emitted when electron goes from the energy state N4 to the ground state. Now here is the ground state, while here is Na4. If we have an electron here, and this electron be excites and gets to this very ground state, then we are asked to calculate the energy difference first, because we are to determine the wavelength. So we have to get the energy involved in moving from E3 to E0, in moving from Na4 to Na1. So we have to get the energy involved. And the energy emitted in falling from higher level here to lower level here should now be the difference between the higher level and the lower level. So at this point, this our E is going to be the energy of higher level minus energy of lower level. That will give us energy difference. That is the energy of photon, or energy liberated in form of electromagnetic radiation. Now the energy of the higher state, the state there is Na4, where we have third excitation energy. So here we have the energy, third excitation energy, that's the higher energy level there, then minus energy at the ground state. Now, the difference there will give us, we do the substitution, where E3 now is minus 0.76 electron volts. then minus, in bracket, we have the ground state energy, which is minus 12.59 electron volts. Then we have to simplify this. Here we have minus 0.76 electron volts. Minus, we open this negative value. Minus minus automatically changes to plus. So we have plus 12.59 electron volts. So at this point, the energy difference now becomes minus 0.76 electron volts plus 12.59 electron volts. Now, punch with me now. Get your calculator. So at this point, we have 12.59 minus 0.76. 12.59 minus 0.76. Now that will give us 11.83 electron volts. And you recall that 1 electron volt has an equivalent value of 1.6 exponential minus 19. 1.6 exponential minus 19. It should be electron volts, should be in joule now. So here we have E equal to 11.83 times 1 electron volt is equal to 1.6 times 10 raised to the power minus 19 joule. So we have to multiply as to get the energy in joule. You see, energy can be measured in joule or electron volt for electrons. So at this point, we have 11.83 times 1.6 exponential minus 19. So we get the final answer for this as 1.89 times 10 raised to power minus 18 joule. So this is the energy liberated by the electron in falling from higher energy level to ground state. But the question says we should find the what? The wavelength. Determine the wavelength of the photon. Now you recall the initial formula I gave to you, where we said that energy of photons is equal to HF. But here we are asked to find the wavelength. Now the frequency, like the second formula there, is equal to C over wavelength. So we are using this very formula. So the wavelength is the one we are now looking for. If you make it the subject of the formula, we have the wavelength equal Hc all over the energy of photons. So at this point, we are going to do the substitution in order to get the value of the wavelength. So we have the wavelength equals, here H is the Planck constant. We have it at 6.6 exponential minus 34. 6.6 exponential minus 34 times C, which is the speed of light, 3 times 10 raised to power 8 all over. We have the energy 1.89 exponential minus 18. The energy 1.89 exponential minus 18. So at this point, we have to simplify. So we have the wavelength equals 6.6 times 3 divided by 1.89 times, here we have 10 raised to the power minus 34 times 10 raised to the power 8 all over 10 raised to the power minus 18. Now we have to simplify this one first. So we have 6.6 times 3 divided by 1.89. So here we have 10.48 times, here we have 10 as the base. You remember the law of indices. So at this point we have 10 raised to the power minus 34 plus 8. Because of this minus 18, we now have plus 18. So the wavelength now becomes 10.48 times 10 raised to power. So we simplify this. Now, minus 34 plus 8 plus 18. Then we are going to have minus 8. Now, when you shift this point back here, then this negative minus 8 will now increase to minus 7. So the wavelength becomes 1.048 times 10 raised to power, we have minus 7. Wavelength is measured in meter. So at this point, I believe I have done justice to the topic. So if this lesson was able to help someone out there, please don't forget to subscribe, share, and turn on notifications for others to learn as well.